Okay, we're going to go over the questions on the gas review worksheet. I will pause at the end of each question slide, and you should at that time pause the video and answer the question, and then come back to the video to see the solution to the question. Okay, we have 3 1-liter flasks at STP, one with ammonia, one with nitrogen dioxide, and the other with nitrogen gas. And it wants to know which of the flasks contain the largest number of molecules. All right, in this question, the thing to remember is that if these gases are in the same size container, they are at the same pressure and the same temperature, that together means that there has to be the same number of moles in each container, which also means there has to be the same number of molecules. So choice D, that all of the flasks contain the same number of molecules, is correct. We have the same situation as in question 1, and here we want to know in which flask do the molecules have the highest average velocity. All right, here, since we're talking about velocity, you want to think about kinetic energy and what affects kinetic energy. Well, in this case, they are at the same temperature, which means they have the same average kinetic energy. All right, and our kinetic energy is 1/2 the mass times the velocity squared, which means that a lower mass is going to give you a higher velocity. So we are looking for the gas molecule that has the lowest mass. Nitrogen is going to be about 28 grams per mole. NO2 is about 46 grams per mole. And ammonia is about 17 grams per mole. So the ammonia is going to have the highest average velocity. So choice A is correct for question 2. All right, number 3. We have 2 samples of the same gas in the same size container with the same pressure. The one in the first container has a Kelvin temperature 4 times that of the gas in the other container. The ratio of the number of moles of gas in the first container compared to that in the second is. All right, so here we have 2 containers, container 1, container 2. They have the same volume, the same pressure, but it says that the temperature in container 1 is 4 times the temperature in container 2. Now, if you remember that pressure is basically a measure of the frequency of the collisions of the particles with the container walls. And so think about what's going to affect the frequency of the collisions. All right. Basically, two key things here that we want to think about is that the kinetic energy of the particles is going to affect how frequently they collide, which that is proportional to the temperature. And the other thing is that the number of moles is going to affect the frequency. You have more particles, you get more collisions. So if the pressure is the same in both containers, then we know the frequency of the collisions is going to be the same. So in order for a container at a lower temperature, in this case container 2, to have the same pressure as a container at a higher temperature, then it has to have more gas particles in it. So the moles of gas in container 2 has to be greater than that in container 1. And in fact, if the temperature in container 1 is 4 times greater, then container 1 needs to have a fourth of the number of molecules that container 2 does in order for them both to have the same pressure. Or, thinking of it in another way, container 2 needs 4 times as many particles to have the same frequency of collisions that is going on in container 1. So the ratio from container 1 to container 2 in the number of moles is 1 to 4, which is choice C. All right, same example as in question 3. Here we want to know the ratio of the number of collisions with the walls in the first container compared to that in the second is. Okay, hopefully you do not have to think about this very hard, and that you remembered that, like I said previously, that pressure is a measure of the frequency of the collisions with the container wall. So if the pressure is the same, that means the frequency of the collisions is the same. And so the ratio of collisions with the wall in the first container compared to that of the second is going to be 1 to 1, which is choice A. Okay, here we have gas sample at constant pressure, occupies 3.62 liters, and has a temperature of 21.6 degrees Celsius. And we want to know at what temperature will the volume of the gas be 3.37 liters. All right, so let's break this one apart. We have an initial volume of 3.62 liters. And we have a second volume of 3.37 liters. I have an initial temperature of 21.6. And that's going to be 294.6 Kelvin. And I want to know what that second temperature is going to be. So 294.6 Kelvin. All right. If my volume is decreasing, then the temperature would have had to decrease also. So I want 3.37 liters over 3.62 liters, and that gives me 294.6 times 3.37 divided by 3.62. I get 274.3 Kelvin, and so that corresponds to choice B. Okay, number 6. We have chlorine in 2 separate containers at the same temperature and pressure. The volume in the first container is 1.3 liters, and it has 6.7 moles of the gas, and the volume in container 2 is 2.64 liters, and it wants to know how many moles of the gas are in container number 2. All right, so if I have, again, here's container 1, container 2, both of them have chlorine in there, and container 1 is 1.3 liters, and it has 6.70 moles of gas, and the volume in container 2 is 2.64 liters, and it wants to know how many moles, and we know that the temperature is the same and the pressure is the same. Okay? The thing to remember here, if we have a case where our temperature and our pressure are the same, that means that the volume ratio is the same as the mole ratio. So we can just say that if I have 1.3 liters to 2.64 liters, 6.7, so the volume ratio is going to be the same as our mole ratio. Okay, and so that gives us 4 times 6.7 divided by 1.3. That gives me 13.6 moles, which is choice A. Number 7, gas sample is heated from -20 Celsius to 57. Volume is increased from 2 liters to 4.5 liters. And if I have a pressure of 0.12 atmospheres, what is the final pressure? Okay, so let's look at this. V1 is 2. V2 is 4.50 liters. T1 is -20. That's going to give me 253 Kelvin. And T2 is 57. And that's 330 Kelvin. And my P1 is 0.12 atmospheres, and I want to know what P2 is. Okay, 0.120 atmospheres. Two things are changing. Okay, let's look at them separately. My volume is increasing, and in response, my pressure will decrease. So I want 2 liters over 4.5 liters there. My temperature is increasing, and in response my pressure will increase. So I want 330 Kelvin over 253 Kelvin. So let's see what we get. We get 0.12 times 2 divided by 4.5 times 330 divided by 253, and I'm getting 0.0696 atmospheres, which is choice B. Okay, number 8. Valve between a 5-liter tank containing a gas at 9 atmospheres and a 10-liter tank containing a gas at 6 atmospheres is opened. Calculate the final pressure in the tanks. All right, here we have 5-liter tank here, valve in between, and a 9-liter tank. 10-liter tank, and at 9, first tank is at 9 atmospheres, and the 10-liter tank is at 6 atmospheres. And it wants to know what the final pressure will be in the tanks. All right, so let's just call these tank 1 and tank 2. And the easiest way to do this is to think about it as a basic gas law problem, that I have two gases that are going to expand into a new volume. And we're going to say that our new volume is going to be 15 liters, that any connection between them has a negligible volume there. So let's look at gas 1. I have a V1 of 5 liters, P1 of 9 atmospheres. Okay, V2 again is going to be 15 liters. So we have 9 atmospheres. My volume is increasing, so my pressure should decrease. So I want 5 liters or 15 liters. So that gas is going to have a new pressure of 3 atmospheres. And then let's look at the same thing over here. This one, my V1 is 10 liters. My V2 is 15. My P1 is 6. And so here I have 6 atmospheres. Again, volume increases, pressure decreases. So I have 10 over 15 liters, and that gives me a new pressure of 4 atmospheres. Dalton's law said that my P total is going to be the sum of the individual pressures of the two gases that are mixing. So my new pressure would be 7 atmospheres, which is choice C. Alright, hydrogen and chlorine gases react to form hydrogen chloride. You and a friend are on opposite sides of a long hallway, you with hydrogen gas and your friend with chlorine gas. You both want to form hydrogen chloride in the middle of the room. Which of the following would be true? Okay. So the key thing here is that our gases, since they're in the same hallway, we're going to assume they're at the same temperature, all right, which means they have, again, the same average kinetic energy, and that the kinetic energy is 1/2 mv squared. So the speed at which it will travel is a function of the mass. Lower mass is higher speed. So let's look at the two gases we have. We have H2, which is about 2 grams per mole. And we have Cl2, which is about 71 grams per mole. So this will move slower. So if you want the gases to meet in the middle of the room, then the friend that has the chlorine gas should release it first, which is choice B. All right, number 10, which conditions of pressure, temperature, and moles, respectively, are most ideal? All right, this question is basically saying under what conditions does the ideal gas law apply so that you can use it rather than the more complex van der Waals equation, okay? The key thing to remember here is that we want conditions where the volume of the gas particles is negligible, which this would imply low pressures, because low pressures are typically a function of a large volume. And in large volumes, the volume of the individual particles would be negligible. The other thing is that we want conditions where there are no interactions, attractions, or repulsions between the particles. And that is going to be, again, low pressures, because we don't want we don't want our particles really crowded together. So low pressures, low numbers of molecules, low moles, and then we also want high temperatures. And the high temperatures is because if they have lots of kinetic energy, their ability to move past each other without having any kind of interaction is greater. So low pressures, low number of moles, high temperatures, which is choice E. Okay. Let's see. Given a cylinder of fixed volume with 1 mole of argon gas, which of the following is correct? And we are assuming that the conditions we're looking at are ideal. All right, so let's look at what we have here. If the temperature, this is A, if the temperature of the cylinder is changed from 25 to 50 degrees Celsius, the pressure inside the cylinder will double. All right, so it says, this says in the question setup, it says that our volume is going to be constant and that our number of moles is going to be constant as well. All right, so this is saying if my temperature, A says that if the temperature increases, that the pressure will increase. And not only will it, well, which is true, but then it says more specifically that it will double. Key thing here to remember is that these relationships are a function of the Kelvin temperature. So my Kelvin temperature is going from 25 Celsius, which is 298 Kelvin, to 50 degrees Celsius, which is 323 Kelvin. Okay, not doubling. Okay, so A would be false. The ratio of the change in the temperatures would be the same as the change in the pressures, and in this case, the temperature is not doubling. The Kelvin temperature, anyway, is not doubling, so the pressure would not double. B, if a second mole of argon is added to the cylinder, the ratio of temperature to pressure would remain constant. Okay. The answer to that is no. If we add more moles, we're going to change the pressure without necessarily changing the temperature. Okay, so our temperature to pressure ratio would not remain constant because the pressure would be affected if we change the number of moles. In C, so B is also false. C, a cylinder of identical volume filled with the same pressure of helium must contain more atoms of helium because helium has a smaller atomic radius than argon. Okay, if we have the same volume of helium and the same pressure of helium, if the pressure is the same, that means the frequency of the collisions is the same. And so we're, I guess, assuming here that the temperature is also going to be the same, identical volume paired with the same pressure, must contain more atoms. I'm thinking with C, we have to assume that the temperature is going to be the same as well. And if that's the case, then no, it wouldn't have to have more atoms of gas. And the fact that helium has a smaller radius doesn't really matter because, again, if it's behaving in an ideal manner, then the volume of the particles is negligible anyway. So E would be the correct choice. All right, here I have 4 identical 1-liter flasks. Each one has a different gas in it, but they're all at the same temperature and the same pressure. Okay, which one has the highest density? Okay, density is mass per volume. All right, and we know that our volume is the same in each case, so we're looking for the one with the greatest mass. And so, and the thing to remember too is that they are at the same pressure and the same temperature, so N is the same moles. That means the one with the highest mass was going to have the greatest density. In that case, chlorine with its mass of 71 grams per mole would be the greatest. So choice B. All right, keep these things in mind because the next questions 13 through 17 are going to use the same setup. Okay, so for the same setup here, for which gas do the molecules have the highest average velocity? All right, remember this is what we talked about before. They're at the same temperature, so our kinetic energy is going to be the same. And since kinetic energy is 1/2 mv squared, the lowest mass would have the highest velocity, and so helium has the lowest mass, so it's going to be the highest velocity. Okay, same setup. Which gas sample has the greatest number of molecules? Remember what we said before? We have, if the volume is the same, pressure is the same, temperature is the same, your moles is the same, which means that number of molecules is the same. So choice E is correct. Then for which gas are the molecules diatomic? Okay, you have to run 5 laps around the school if you missed this question. The answer is B. Diatomic means it has 2 atoms of the same type in the molecule, and chlorine is the diatomic gas among those listed. 16. Same setup. For which gas are the collisions elastic? Okay, here our conditions stated are the 0 degrees Celsius and 1 atmosphere. They are at STP, and STP conditions imply an ideal behavior, and based on the kinetic molecular theory says that the collisions are elastic, meaning there aren't any interactions between the particles that would, one of them's not going to absorb energy, or there's not going to be energy lost in the collisions. Number 17, for which gas do the molecules have the smallest average kinetic energy? Same temperature means the same average kinetic energy. So, choice E. Okay, in order that this podcast is not so long that you can't download it, I'm going to break it apart, and we will continue in a second video for